Industrial fishing operations in the Bering Sea represent one of the most technologically sophisticated, economically significant, and physically demanding forms of seafood harvesting in the world. Understanding this industry requires examining multiple interconnected dimensions: the biology and ecology of the target species, the vessels and technology employed to locate and capture fish, the economics driving these expensive operations, the onboard processing systems that transform raw catch into consumer products, the human experience of working in extreme conditions, and the regulatory frameworks attempting to ensure long-term sustainability of fish populations and the communities that depend on them. Alaska pollock, scientifically known as Gadus chalcogrammus and sometimes called walleye pollock, ranks among the most abundant fish species on Earth and one of the most commercially important in terms of total catch volume. These fish belong to the cod family Gattidae and inhabit the cold waters of the North Pacific Ocean, with particularly large concentrations in the Bering Sea, the body of water between Alaska and the Russian Far East that connects the Pacific Ocean with the Arctic Ocean through the Bering Strait. Pollock are mid-water schooling fish, typically found at depths between 100 and 300 meters, though they exhibit significant vertical migration patterns moving up and down in the water column in response to prey availability, light conditions, and other environmental factors. They form dense schools that can contain millions of individuals, a behavior that evolved as protection against predators through the dilution effect. Predators can only eat so many fish, so being part of a massive school increases individual survival probability. This schooling behavior, while beneficial for the fish evolutionarily, makes them vulnerable to modern industrial fishing methods that can locate and capture entire schools. The biology of Alaska pollock makes them particularly suitable for supporting large-scale commercial fisheries. They grow relatively quickly by fish standards, reaching sexual maturity at 3 to 4 years of age and commercial harvest size shortly thereafter. They reproduce prolifically through broadcast spawning, with females releasing hundreds of thousands of eggs into the water column where they're fertilized externally by sperm released by males. This high fecundity, the capacity to produce large numbers of offspring, means that pollock populations can potentially sustain substantial fishing pressure if management prevents overfishing and allows sufficient reproductive individuals to survive and spawn. However, this reproductive capacity doesn't guarantee sustainability. Pollock populations have experienced dramatic fluctuations over recent decades, with periods of high abundance followed by steep declines that have triggered economic disruption in fishing communities and companies dependent on pollock harvests. These fluctuations result from complex interactions among fishing pressure, environmental conditions affecting spawning success and juvenile survival, predation by marine mammals and other fish, and competition for food resources. Understanding and predicting these population dynamics remains challenging despite sophisticated scientific monitoring and modeling efforts. Pollock occupy a crucial intermediate position in North Pacific marine food webs. They feed primarily on zooplankton, tiny drifting animals including copepods, krill-like euphausiids, and larval stages of various marine organisms. By consuming these small organisms in enormous quantities, pollock schools convert dispersed plankton into concentrated fish biomass. In turn, pollock serve as prey for numerous larger predators, including several seal and sea lion species, larger predatory fish, such as Pacific cod and halibut, and various seabirds. Changes in pollock abundance therefore ripple through entire ecosystems, affecting both the prey organisms they consume and the predators that depend on them for food. The commercial value of pollock derives from the versatile nature of their white flesh and the variety of products that can be manufactured from different parts of the fish. Pollock fillets appear in restaurants and retail markets in numerous forms, including breaded fish sticks, fish sandwiches at fast food chains, frozen fillet portions, and various prepared fish products. The relatively bland, mild flavor and firm white flesh make pollock acceptable to consumers who might reject stronger flavored fish species. Perhaps even more important economically is surimi production. Surimi is a processed fish paste created by mechanically separating fish flesh from bones and skin, washing it repeatedly to remove fats and proteins that cause discoloration, then mixing it with stabilizers and cryoprotectants that allow it to be frozen and later reformed into various shapes. Surimi manufactured from pollock serves as the base ingredient for imitation crab meat, artificial lobster, and numerous other analog seafood products that are particularly popular in Asian markets. The global surimi industry depends heavily on Alaska pollock as its primary raw material source. Pollock roe, the egg masses from female fish, commands premium prices in specific markets, particularly in Japan, where it's known as mentaiko or tarako, depending on preparation. The roe can sell for $20 to $60 per pound or even higher for premium grades, making it far more valuable per unit weight than the fish flesh. For fishing operations, row recovery represents crucial revenue that can mean the difference between profitable and unprofitable voyages. Even the portions of pollock not used for human consumption have commercial value. Fish heads, frames, viscera, and processing waste are rendered into fish meal, a protein-rich powder used in animal feeds, particularly in aquaculture, where farmed fish are fed pellets, manufactured partially from wild-caught fish meal. Fish oil extracted during rendering has various industrial and nutritional supplement applications. Modern pollock fishing operations utilize nearly every part of the fish, minimizing waste both for economic reasons and to address environmental concerns about discarding organic material. The vessels that harvest pollock in the Bering Sea are extraordinary pieces of industrial engineering that combine fishing capabilities with onboard processing facilities of a scale and sophistication comparable to land-based food processing plants. The largest factory trawlers exceed 100 meters in length and can displace 5,000 tons or more. These vessels are equipped with diesel engines producing 5,000 to 8,000 horsepower or more, sophisticated navigation and fish-finding electronics, massive hydraulic systems for deploying and retrieving fishing gear, and extensive processing facilities below deck. The economics of constructing and operating such vessels are demanding and create the fundamental pressures that shape operational decisions. Modern factory trawlers represent capital investments of $50 to $150 million depending on size and capabilities. Operating costs are substantial and ongoing. Fuel consumption can exceed 10,000 gallons per day during active fishing operations. Crew wages for 100 to 150 workers represent significant expense. Maintenance of complex mechanical and electronic systems requires constant attention and periodic major overhauls. Insurance costs for vessels operating in dangerous waters are considerable, and regulatory compliance, including observer programs and monitoring systems, adds additional costs. These high fixed costs create powerful economic imperatives to maximize catches and operational efficiency. A vessel that costs $75,000 per day to operate must catch and process enormous quantities of fish simply to break even, let alone generate profit. This economic reality drives decisions about when and where to fish, how long to continue operations in marginal conditions, and how intensively to push crews and equipment. The tension between economic pressure to maximize catches and biological/regulatory limits on sustainable harvest levels represents a fundamental challenge in industrial fishing management. The fishing technology employed centers on midwater trawl nets, enormous bag-shaped nets constructed from synthetic fibers and towed through the water column at depths where target fish species congregate. Modern trawl nets used in Bering Sea pollock fishing are genuinely massive structures. The net opening, the mouth through which fish enter, can exceed 50 meters in both width and height, creating an opening area of over 2,000 square meters. The net itself can extend 200 to 300 meters behind the vessel, tapering gradually to the cod end where fish accumulate as they're swept backward by water flow through the net. The nets are held open by large trawl doors, steel or composite structures weighing several tons each that use hydrodynamic forces to spread apart as the vessel moves forward, maintaining the net mouth in an open configuration. These doors are connected to the vessel by heavy steel cables that also transmit the immense forces required to tow the entire system through the water. The engineering required to design systems that can reliably handle these forces while operating in severe sea conditions represents significant technical achievement. Advanced sonar and acoustic systems have revolutionized the efficiency of locating and capturing fish. Hull-mounted sonar systems scan large volumes of water, detecting fish schools and providing information about their size, density, depth, and movement. Modern systems can distinguish between different species based on the acoustic signatures produced by their swim bladders, the gas-filled organs that help fish maintain neutral buoyancy, but also make them excellent acoustic reflectors. This capability allows vessels to target specific species while avoiding non-target fish that might be subject to bycatch restrictions. Net-mounted sensors provide real-time information about fishing operations in progress. These sensors monitor the net's shape and position, detect when fish are entering the net, and estimate the quantity of fish being captured. This information allows captains to optimize towing speed, direction, and duration to maximize catches while avoiding overfilling the net, which could cause it to tear or allow fish to escape. The technology essentially allows continuous monitoring of fishing effectiveness, enabling rapid adjustments to changing conditions. The combination of sophisticated fish-finding technology with efficient capture systems has dramatically increased fishing power, the ability to locate and harvest fish, compared to historical methods. A modern factory trawler can catch in hours what might have taken weeks or months using earlier technology. This increased efficiency creates both economic benefits through reduced costs per unit of fish caught and conservation challenges because it's now possible to overexploit fish populations if catch limits aren't carefully set and enforced. The onboard processing facilities on factory trawlers represent sophisticated industrial operations that must function reliably while dealing with constant motion from waves, exposure to corrosive salt water, and the challenge of processing highly perishable raw material. The systems are designed for high-speed automated processing with minimal human intervention except for quality control and tasks requiring judgment or manual dexterity. The process begins when fish are pumped or conveyed from holding tanks where they're stored after being brought aboard. Automatic sorting systems separate fish by size using mechanical grading equipment that passes smaller fish through progressively larger gaps, while larger fish continue on separate conveyor lines. This size sorting is crucial because different sizes require different processing approaches and may have different end uses or market values. Mechanical heading and gutting machines remove heads and viscera at high speed. The most advanced systems can process 800 to 1,000 fish per minute. The machines use precisely positioned blades that cut at specific anatomical locations, leveraging fish anatomy's predictability to achieve consistent results. The separated heads and viscera are diverted to waste processing systems rather than being discarded overboard, both to recover valuable products like roe and to minimize organic pollution. Filleting machines employ multiple blade assemblies that make sequential cuts to separate flesh from bones and skin. The process involves cutting along the spine, removing rib sections, trimming fins, and producing uniform fillets, meeting specific size and quality parameters. The precision required is substantial because errors reduce product value. Meat left on bones represents lost revenue, while bones remaining in fillets create quality problems. Following mechanical processing, fillets pass quality inspection stations where workers examine each piece, removing any defects including remaining bones, parasites, discolored tissue, or damaged sections. This manual inspection remains necessary despite automation because visual and tactile assessment of food quality still exceeds machine capabilities for detecting subtle problems. The workers performing this inspection must maintain focus while processing hundreds of fillets per hour in cold, wet conditions, demanding work requiring sustained attention. After inspection and trimming, products move to freezing systems. Plate freezers are commonly used for fillet products. These systems sandwich product between metal plates cooled to -35 degrees Celsius or colder, rapidly freezing the fish. Speed of freezing matters because slow freezing forms large ice crystals that damage cellular structure, creating mushy texture when thawed. Rapid freezing creates smaller ice crystals that preserve texture and quality. The frozen products are then packaged in branded boxes with date codes and traceability information, allowing customers to track products back to specific fishing operations. The human dimension of pollock fishing involves substantial physical and psychological challenges that make it among the most demanding occupations in terms of working conditions. Crews on factory trawlers typically work 12 to 18-hour shifts 7 days per week for periods extending 2 to 4 months continuously at sea. There are no days off, no weekends, no break from the work routine except when weather conditions prevent fishing operations or when quotas are reached and the vessel returns to port. The work is physically demanding in ways that accumulate over time. Factory workers stand continuously on concrete floors that are wet and often moving from the vessel's motion. The repetitive motions of processing fish, cutting, trimming, handling product, create chronic strain on hands, wrists, arms, and backs. The cold temperatures required for fish processing mean workers are constantly chilled despite protective clothing. The noise from machinery, hydraulic systems, and the vessel's engines is constant and requires hearing protection that makes communication difficult. The environment presents numerous safety hazards. Mechanical processing equipment includes sharp blades moving at high speed. Conveyor systems have pinch points that can catch clothing or body parts. Floors are wet and slippery despite textured surfaces and drainage systems. The vessel's motion can cause workers to lose balance, potentially falling into machinery or onto hard surfaces. Fatigue from long shifts and sleep deprivation increases accident risk by reducing reaction time and situational awareness. The psychological challenges stem from multiple sources. Extended separation from families and normal social relationships creates stress and emotional strain. The absence of privacy aboard vessels where workers share small cabins and have limited personal space wears on people accustomed to more autonomy. The monotony of performing the same tasks repetitively for months can be mentally exhausting. The lack of typical temporal rhythms, weekends, days off, variation in routine, creates disorientation that some workers find profoundly difficult. Sleep deprivation represents a persistent challenge because the work continues around the clock in shifts. Workers typically have 6 to 8 hours between shifts, but this includes time for eating, hygiene, and any personal activities, leaving insufficient time for adequate sleep. The cumulative sleep deficit that develops over weeks and months of this schedule affects cognitive function, mood, and physical health. Studies of shift workers consistently show negative health outcomes associated with disrupted circadian rhythms and chronic sleep insufficiency. The compensation offered for this demanding work reflects the challenges involved. Entry-level factory positions might earn $40,000 to $60,000 for a season lasting several months, substantial income for young workers without advanced education or specialized skills. The lack of opportunities to spend money while at sea means workers can accumulate savings rapidly. Skilled positions, including engineers, factory supervisors, processing equipment technicians, and deck officers, earn significantly more, potentially $80,000 to $120,000 or more per season. The captain and senior officers receive compensation, reflecting their responsibilities for vessel safety, catch success, and regulatory compliance, potentially exceeding $150,000 annually. For many workers, particularly those from economically depressed regions with limited employment opportunities, the income available from fishing work justifies the difficult conditions. Young people can earn in a few months what might take a year in land-based employment. This creates recruiting advantages for the industry despite the challenges, though retention remains problematic because many workers leave after 1 or 2 seasons once they experience the reality of the working conditions. The Bering Sea environment itself adds another dimension of challenge. Weather conditions in the Bering Sea are notoriously severe and unpredictable. The collision of Arctic air masses from the north with warmer air from the south creates powerful storm systems that can develop rapidly. Wind speeds during storms can exceed 100 kilometers per hour, creating waves that can reach 10 to 15 meters in height. Even large vessels are affected by such conditions. They pitch and roll violently, making all activities more difficult and dangerous. Water temperatures throughout the year remain near or below 5 degrees Celsius, cold enough that anyone who falls overboard has only minutes before hypothermia causes incapacitation. Survival in Bering Sea waters without immediate rescue is unlikely. Ice formation on vessels during winter represents a serious hazard because accumulated ice reduces stability and can lead to capsizing if not continuously removed. The geographic remoteness means that medical emergencies, equipment failures, or vessel casualties cannot be quickly addressed. Assistance is days away even in good weather. The regulatory framework governing Bering Sea pollock fishing is complex, restrictive, and represents one of the more successfully managed large-scale fisheries globally, though challenges and controversies persist. The North Pacific Fishery Management Council, operating under the Magnuson-Stevens Fishery Conservation and Management Act, establishes regulations including annual catch limits based on stock assessments conducted by fishery scientists from NOAA's Alaska Fisheries Science Center. These stock assessments synthesize multiple data sources, including acoustic surveys that estimate fish abundance and distribution, trawl surveys that sample fish populations, catch data from commercial fisheries, biological samples providing information about age structure and growth rates, and oceanographic data about environmental conditions. This information feeds into population models that attempt to estimate total biomass, reproductive potential, natural mortality rates, and sustainable harvest levels. The models involve substantial complexity and incorporate numerous assumptions, meaning the estimates carry uncertainty that must be accounted for in management decisions. Based on these assessments, the Council sets an acceptable biological catch representing the sustainable harvest level, then typically applies additional precautionary reductions to establish the total allowable catch that will actually be permitted. This TAC is then allocated among qualified vessels or companies through catch share systems where participants hold percentages of the total allocation. These allocation shares can be bought, sold, or leased, creating economic incentives for efficient operations, since unused allocation represents lost income opportunity. Extensive monitoring and enforcement systems ensure compliance with regulations. All large vessels must carry trained fisheries observers who monitor catches, document bycatch of non-target species, collect biological samples, verify that fishing occurs in permitted areas, and provide independent verification of vessel reporting. The observer coverage is among the most extensive in global fisheries, providing high confidence in catch accounting. Electronic monitoring systems using cameras are also being implemented to supplement human observers. The sustainability of Bering Sea pollock populations under this management regime appears reasonably good compared to many global fisheries, though concerns persist. The population has fluctuated substantially, with periods of low abundance triggering catch reductions that created economic hardship for industry and dependent communities. Climate change introduces additional uncertainty through effects on ocean temperature, water column structure, prey availability, and predator-prey relationships that may affect pollock recruitment and distribution in ways not fully understood or predictable. The products derived from Bering Sea pollock reach consumers through remarkably extensive and efficient distribution networks. Fast food chains are major buyers. The fish used in fish sandwiches at McDonald's, Burger King, and similar chains comes predominantly from Alaska pollock. Retail products sold in supermarkets including fish sticks, breaded fish portions, and frozen fillets rely heavily on pollock. The surimi manufactured from pollock appears globally in Asian restaurants and markets as imitation crab, lobster, and other analog seafood products. This global distribution means that industrial fishing operations in the remote Bering Sea directly connect to food choices made by consumers worldwide who typically have no awareness of the origins of their food. The efficiency and scale of modern pollock fishing makes affordable seafood protein available to millions of people who might otherwise have limited access to fish products. Whether this represents sustainable use of marine common pool resources or exploitation that will ultimately prove unsustainable remains subject to debate, though the Bering Sea pollock fishery is generally regarded as better managed than many alternatives. The future of Bering Sea pollock fishing will be shaped by intersecting factors, including climate change impacts on fish populations and marine ecosystems, regulatory decisions about harvest levels and management approaches, market demand for pollock products in competition with aquaculture and other protein sources, technological changes affecting fishing efficiency and processing capabilities, and broader societal questions about the sustainability and ethics of industrial-scale exploitation of wild marine resources. The contrast between the harsh conditions workers endure and the mundane products consumed by people who never consider the origins of their food highlights fundamental disconnections in modern industrial food systems. The fish sandwich purchased casually represents the culmination of extraordinary effort by workers in dangerous conditions, deployment of sophisticated and expensive technology, careful management of natural resources, and complex logistics moving product from one of Earth's most remote environments to consumers worldwide. Understanding these connections provides perspective on both the remarkable capabilities of modern industrial systems and the often hidden costs of abundance and convenience.